These are examples for section 14.7, dimensional changes in space. Example 1. Are the two rectangular prisms similar? If so, what is the scale factor of the first figure to the second figure? Here we have two prisms, and they're asking if they are indeed similar. They look similar, but to find out for sure, we need to take all the dimensions they offer. In this case, there's three: the heights, the widths of the bases, the lengths of the bases, or base and height, and see if they form the same ratio. So to do that, we'll start with the first figure. 3, the height. We'll start with the height of the smaller one to the height of the larger one, 3 to 6. I'm going to check to see if that's equal to the length of the base here in the first one, which is 2, to the length of the base here, which is 4. See if that's equal to the width. 3 here is to the width over here, 6. All the corresponding edges or all the corresponding dimensions. And of course, when we reduce all three of these, if we get the same fraction, then they're similar. So 3 6 reduces by 3. 3 goes into 3 once. 3 goes into 6 twice. 2 4 reduces by 2. 2 goes into 2 once. 2 goes into 4 twice. And 3 6, of course, already reduced to 1/2. All 3 times we get 1/2. Therefore, figures are similar. And K, which is our scale factor, is 1 to 2. And the reason why we're writing 1 to 2, not 2 to 1, is because they asked for the first figure to the second. And that's what we did. Part B, the directions are these two cones similar? If so, what is the scale factor of the first to the second? This time we've got the larger one first, the smaller one second. They look similar, but to make sure of that, we've got both our heights that are supposed to correspond in both figures, and in the base, all we need is the radius since it's a circle. So we only have 2 to check, 2 ratios. So I'm going to start with the radius of the base here with the first one is to the radius of the base here, 3 to 1, and see if that's equal to the height in the first cone, which is 15, to the height of the cone in here, which is 6. 3 ones doesn't reduce. 15 6 does reduce by 3. 3 goes into 15 5 times. 3 goes into 6 2 times. And so as you can see, 3 to 1 does not equal 5 to 2. Therefore, not similar. These are not similar figures. And so there's no K. No scale factor. Example 2. The square prisms below are similar. What is the scale factor of the smaller prism to the larger prism? So, what do we know? We know these are similar. We also know the volumes of both. They're asking us for the scale factor, which is K. So if we've got both the volumes, we can write the VR, or volume ratio. So when we have the volume ratio, we're looking for K, we're going to end up taking the cube root of the volume ratio. So first of all, number 1, since both volumes are given, find and simplify the volume ratio. So starting with the small one, we simply write a fraction or ratio with the volume. So we have the volume ratio is 1,458 square centimeters or cubic centimeters to 2,662 cubic centimeters volumes. Cubic centimeters divide out and we get 1,458 to 2,662. This ratio will reduce at least by 2 because these are even, so we reduce by 2. And when we divide 1458 by 2, we get 729. Dividing 2662 by 2, we get 1,331. And we can't reduce this any longer, so this is our VR, our volume ratio. The next thing we want to do is find or establish K. To find K, we take, as I said earlier, the volume ratio and take the cube root of it. That'll get us back to K. So we take the volume ratio that we have after we simplified, 729 to 1,331, and take the cube root, which means we take the cube root of the top number, the numerator, in the first term, and we take the cube root of the second term, or denominator. When we do that, take the cube root of 729, it's a perfect cube, we get 9. And 1,331 is a perfect cube, we get 11. Therefore, K is 9 to 11, smaller to larger. Example 3, painting. The lateral areas of two similar paint cans are 245 square centimeters and 80 square centimeters. So what we are given are the lateral areas of these two. We've got surface area of the larger one, 245 square centimeters, and the surface area of the smaller one, which is 80 square centimeters. And of course, this is actually lateral area. Now, whether it's lateral area or total surface area, it doesn't really matter because it's area, it's two-dimensional. So we will be using the area ratio regardless of what kind of areas. So we've got the two lateral areas. The volume of the smaller can is 192 cubic centimeters. So we have the volume of the smaller can. What is the volume of the larger can? So since we're looking for the volume and we're given the surface or some type of surface area, we're going to have to go from surface area or lateral surface area back to the scale factor, then take the scale factor and go to the volume or volume ratio in this case. So to start off with, number 1, since we have both lateral areas, write and simplify the AR, or area ratio. To do that, it doesn't really matter in this problem whether we use the small to large or large to small, because they're asking us for the volume of the larger can. So whether we write it one way or the other doesn't matter. So I'll just start with the first one, start with the larger one. So for our area ratio, since that's what we're given in both, it's 245 square centimeters to the lateral area of this one, 80 square centimeters. The square centimeters divide out and we get 245 to 80. Notice both these numbers are both divisible by 5, so let's reduce by 5. Now remember, this is still the area ratio. We haven't started finding K yet. 245 divided by 5 is 49. 80 divided by 5 is 16. And that's as far as we can reduce that. That's our area ratio, simplified. So now that we've done that, we've simplified it, the second thing we do is we establish or find K. We've got to go back to K, which is the scale factor. To find K, when we have the area ratio, we have to take the area ratio and take the square root of it. So we take the square root of our area ratio, 49/16, which means we can take the square root of the top number, or first term, over the square root of the second term. The square root of 49 is 7, and the square root of 16 is 4. So our scale factor K is 7 to 4. Now that we have the scale factor, we're looking for volume, so we need our volume ratio now. So third, we find or use K to find the volume ratio. Finding the volume ratio means we have to take K and cube it. And you may ask, why don't we just go from area ratio to volume ratio? Because we can't. We have to go through K to do this. So the volume ratio is K cubed, and since K, the scale factor is 7 to 4, we cube it. Which means we cube the numerator and the denominator. 7 cubed, or 7 times itself 3 times, gives us 343. 4 cubed gives us 64. So this is our VR, or volume ratio. The last thing we do, number 4, is we use the VR to set up proportion and find missing volume. So we take our VR, 343 to 64, set up a proportion using the volume we're given, which is the small can, which means it's across from the smaller VR number, 192 cubic centimeters. And in the top, we're going to use a variable, I'll just use x, cubic centimeters for the volume, the one we're asked to find. At this point, we can cross multiply. This is a proportion. We get 64x equals 343 times 192. It gives us 65,856. Dividing both sides by 64 to solve for x, we get x is equal to exactly 1,029 cubic centimeters. So the volume of the larger can is 1,029 cubic centimeters. Example 4, containers. A bottle that is 10 inches high holds 34 ounces of milk. The sandwich shop shown at the right is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could the actual building hold? Which is something you probably wouldn't do in real life. It's just kind of an interesting problem. But the bottle, let's assume the bottle is similar to the actual bottle that you buy at this particular shop. So they want to know how much milk will fill this up. Well, then we're talking about capacity. And capacity includes, when we find volume, that is capacity. Now, how much will this container hold? That's volume. When they talk about gallons here, equal to so many ounces, that's also capacity. So the ounces here aren't the kind, it's not weight ounces, this is capacity ounces. There's 128 ounces in 1 gallon. So when we do this problem, keep that in mind. The very first thing we want to do is write the scale factor. We'll start with the scale factor. So number 1, write simplified K, or scale factor. So to do that, we need the two corresponding dimensions in both the bottle and the building. Well, it looks like we have the height, if you can see it on your paper there. 480 inches high is the shop's height. They put it in inches for us. So they've got 480 inches, and the height of the actual bottle of milk is 10 inches. And they're both in inches, so we can write our scale factor, K. It doesn't really matter where the small comes first or second, since they're asking us how much volume that we're going to find in this. So I'm going to just use the small bottle first. So that's 10 inches for the height to the height of the building, which is 480 inches. Well, the inches divide out, and we get 10 over 480. And of course that reduces by 10, and we get 1 to 48. So this would be our K. Our scale factor is 1 to 48. The building is a lot bigger. Next, since we're going to find the volume or capacity in cubic measurement here, so we can talk about how many gallons or ounces here, we are going to need to find the volume ratio. So find the volume ratio. So to find the volume ratio, having K means we're going to have to cube K. So we take K, 1 to 48, and cube it, which means we cube the numerator and cube the denominator. 1 cubed is 1 times itself 3 times, which gives us 1. And 48 cubed, rather large number, is 110,592. So this is our volume ratio. Now that we have the volume ratio, third thing we do is find what they're asking for, basically. First the ounces, and then we'll find gallons. The ounces, we'll underline ounces there, of milk in the building or shop. And we do that by finding, you're using the VR. So we use 1 is to 1,000 or 110,592 and set it equal to another ratio using what we know about how much the smaller bottle will hold. Its capacity is 34 ounces, so it obviously goes across from the smaller one, 34 ounces, OZ. And we want to know how many ounces that is going to be in the building, which is across from the larger volume ratio number. We'll just use X. So cross multiply, 1 times X is X, and 34 times 110,592 is 3,760,128 ounces of milk. Okay, so that's how many ounces this whole building will hold of milk. It's a lot of milk. But they asked for it in gallons, so they gave us a conversion factor. So the last thing we're going to do, we're going to convert our answer to gallons. So we're going to use a conversion factor, which means we're going to multiply a fraction in the form of one fraction in another form. So we're going to start off with what we were given in ounces, 3,760,128 ounces of milk, and we're going to multiply it with a conversion factor. 1 gallon equals 128 ounces. We want to get rid of ounces here, so we put ounces down here. So that means 128 would go down here for 1 gallon up here. The ounces divide out, and of course we're going to get 3,760,128 gallons now over 1 times 128 is 128. Ounces are gone. So we now, of course, we divide. When we divide, we get 29,376 gallons of milk in the building. All right, in the shop. Now, that's a lot of milk. Well, they also asked us to round the amount of ounces to the nearest 1,000. So we're going to do that also. That's one answer. So we're going to take this, what we found in ounces, and round to the, they asked for the 1,000, nearest 1,000. So the 1,000th place is here. Here's the next place. This is 1, so this stays the same. These become zeros. So our other answer is approximately 3,760,000,000 ounces. That's how many ounces rounded. Example 5. How is the volume of the cylinder pictured down below affected if the height of the cylinder is multiplied by 3 and the radius is multiplied by 2? Okay, so they're referring to the smaller one here, because if it's affected by multiplying by 2 different numbers, it's obviously going to get bigger. So here's our original, and they want to know how the cylinder is being affected once it changes its dimensions to this size. And so when they ask how it's affected, of course in this problem we're multiplying by 2 different numbers, which means this is not proportional. It's non-proportional change. So we're going to have to find the volumes of both. And when they talk about being affected, if they're not specific, we always talk about how many more or less times, or how many times bigger or smaller. So we're going to end up probably dividing. So first things first, number one, we need to find both volumes. So find both. We have to find both because it's not proportional. Volumes. So I'm going to let this one be my first cylinder and my second cylinder. So let's write V1 and V2. So volume sub 1, big BH, it's a cylinder, where big B is pi r squared. Pi r squared times h. So here our radius is 4, so we have pi times 4 squared times the height, which is 12. 4 squared is 16 pi times 12. And 16 times 12 is 192. So 192 pi cubic centimeters. We leave pi here so we can compare a lot more efficiently. Now the volume of my resulting cylinder over here, notice there's no dimensions, but we can figure out what that's going to be by using the numbers up here. So again, that's big BH, which of course is pi r squared h. So what we're going to do is we're going to take our pi down. Our radius, instead of using just 4, since it said we take our radius and multiply it by 2, we're going to do this. We take our radius, original, 4, and multiply it by 2. And that's squared. Times the height. Well, our new height's going to be our old height, 12, times 3. So there are the two changes. Now we simplify. So as we simplify, let's see, 4 times 2, we have pi times 4 times 2 is 8 squared, times 12 times 3 is 36. And then 8 squared is 64 pi times 36. And 64 times 36 is 2,304 pi cubic centimeters. So the volume's gone from 192 pi to 2,304 pi cubic centimeters. So now we can compare to see how they're affected. We do this by dividing. Another way to do that is just to create a ratio of the two different change from one to the other. So we can write the larger one, 2,304 pi cubic centimeters, and divide, remember we're dividing here, by 192 pi cubic centimeters. You just take this and divide by that. Well, obviously those divide out, and we have 2,304 divided by 192. This is going to tell us how many times bigger this one is than this one. So when we divide that, we get 2,304 divided by 192 is 12 times more volume. So this one, the new one, has 12 times more volume than the old one. Now, what do you notice about this number and these two numbers? Think about it. Example 6. The volumes of two similar spheres, these are similar already, are 162 pi cubic inches and 3,072 pi cubic inches. So volume of the smaller one, obviously, and the volume of the larger one. What is the surface area of the smaller sphere? And that's supposed to be if the surface area of the larger sphere is 512 pi square inches. Okay, so this one's going to be a little like one we did a little earlier, except with spheres. This time also we have the volumes, both volumes, so we're going to come up with the volume ratio. Go back to K, scale factor, and then have to go back up to surface area to find this. So number one, we given both volumes, we find and write and simplify the volume ratio, since we have both volumes. So volume ratio, doesn't matter which comes first in this problem. I'll start with this first one here, the smaller one. 162 pi cubic inches to 3,072 pi cubic inches. The cubic inches divide out, the pi's divide out, we get 162 over 3,072. Now let's see if we can reduce this as much as we can. It's reducible by 2. It's also reducible by 3 when you add the digits here. That number is divisible by 3. When you add the digits here, that number is divisible by 3. Therefore, these are divisible by 6. So when I divide by 6 up here, the volume ratio, I get 27. And 3,072 divided by 6, the bottom number, I get 512. This is our volume ratio. Number 2, now that we have our simplified volume ratio, we can now find K, or establish K, the scale factor. Got to go back to K. So K, when you're given the volume ratio, you have to take the cube root of the volume ratio. So we take the cube root of 27 to 512. That means we can take the cube root of 27 over the cube root of 512. The cube root of 27 is 3, and the cube root of 512, another perfect cube, is 8. So this is K. We found our K, or scale factor. This is 3 to 8. That means the radius is 3. It's not necessarily 3, but the ratio of the radius, the radii from this one to this one, is 3 to 8. So we take our K now, and we need to find the surface area, so we're going to go to AR, the area ratio. So use K to find the area ratio. So to find the area ratio, using K, we have to square it. We square K. Take K, 3/8, and square it, which means we square the numerator and the denominator. 3 squared is 9, and 8 squared is 64. So this is our area ratio. Now that we have our area ratio, and we've got one of two areas in our similar figures, we can find the other surface area by using a proportion. So final step, use the AR, set up, proportion, and find missing surface area. So to do that, we use their AR, which is 9 to 64, equals, and then we want our smaller measurement on top, since 9 is on top, so that's the one we're looking for surface area. So I'll write X, it's in square inches, over our larger surface area, which is represented by 64, is 512 pi square inches. Now don't forget your pi. Now we can cross multiply. 64 times x is 64x, and 9 times 512 pi is then 4,608 pi. Dividing both sides by 64, we do that and we get 72 pi square inches. So the surface area of this sphere, of the smaller sphere, is 72 pi square inches. We found the surface area.